Which of the following represents a saturated hydrocarbon? So a question like this, a saturated hydrocarbon will follow the formula CnH2n plus 2, which is the formula for alkanes. So I'm going to go through the options: C2H4, no; C3H6, no; C3H8. That does follow the formula CnH2n plus 2, so the answer is going to be C. Question 1.2. Which of the following pairs of reactants can be used to prepare the ester called ethyl propanoate? So if I look at the name ethyl propanoate, the first part comes from the alcohol. So the alcohol is going to be ethanol. That's the alcohol. And the second part is from the carboxylic acid. And the carboxylic acid is going to be propanoic acid. And so that option is C. Question 1.3. Consider the reaction represented by the equation below. What type of reaction is represented above? So here, I'm going to draw the structural formula. So CH3, CH, CH2. So CH3, so that's the CH3. Then CH, and then CH2. So this must be a double bond. So I'm going from an alkene to a what? Now let's take a look at this formula. So CH3, then there is a CH, then there is a Br, and then there is a CH3. So I'm going to an alkane. So when you go from an alkene to an alkane, you are going from a 2 to a 1, 2 meaning a double bond, and 1 meaning single bonds. So this must be an addition reaction. And if you're looking at the addition reactions, what type of addition reaction would this be? So you are adding a hydrogen. So we've added a hydrogen here. And we are also adding a halogen. So the answer is going to be D, hydrohalogenation. Question 1.4. Consider the following compound. The IUPAC name of this compound is. Again, it'd be easiest if we just draw it. So what we'll do here is we'll start with the CH3. So CH3, then CH, then there is a Cl attached to it, then a CH2, then a carbon that is attached to 3 CH3s. Now if we wanted to name this, we obviously, since it's an alkane, everything, there is no priority here. So we'll just start numbering from the closest branch. So we can start numbering this way, here. And so if I do that, I'm going to have a 1, 2, 3, 4, 5 carbon chain. So it's going to be pentane. Then I have a 2, 2 dimethyl. And then I have a 4 chloro. Now we just need to put all of this together. C comes before M. So it's going to be 4 chloro first. Then 2, 2 dimethyl pentane. And that option is D. Moving on, question 1.5. Two learners want to investigate the factors affecting the rate of the reaction between magnesium and hydrochloric acid. The concentration of the acid remains the same. Which of the following changes to the experiment will produce the fastest rate of the reaction? So powdered magnesium with hydrochloric acid at room temperature, powdered magnesium with hydrochloric acid at a higher temperature. So this one is going to be more promising because it's at a higher temperature, and we know that temperature is one of the factors affecting rate. Option C, magnesium ribbon this is not going to work because powder has a larger surface area, and so it's going to have a quicker rate. Magnesium ribbon, so D is out. The only option that's going to be left is going to be B. So 1.5, the answer is B, and it's because it has the largest surface area, powdered magnesium, and it has a high temperature. Moving on, question 1.6. Consider the energy profile graph for a reversible reaction shown below. The following statements are given. So A minus C represents the activation energy for the reverse reaction. Delta H for the reverse reaction is A minus B. A catalyst lowers the activation energy for both forward and reverse reaction. So the correct statements are what? Okay, let's go through one by one. So if we want to check point 1, A minus C represents the activation energy for the reverse reaction. So if I had to just sketch this out again here. So reverse reaction means we're reading it this way. Activation energy is going to be the energy that's here. So this is going to be reactance. And this is going to be the value C. And this is going to be the value B. So if we want to check the activation energy for the reverse reaction is going to be C minus B. So point 1 is incorrect. Point 2, delta H for the reverse reaction is A minus B. So remember, if that's my reverse reaction, delta H is products minus reactants. So it's going to be A minus B. So point number 2 is correct. Point number 3, a catalyst lowers the activation energy for both forward and reverse. That is correct as well. So only 2 and 3 are correct. So the answer there is A. Moving on, question 1.7. The reaction of an acid-base indicator represented as HIN with H2O reaches equilibrium according to the following balanced equation. Okay, so we have the equation. At equilibrium, the color of the solution is red. Which of the following will change the color of the solution from red to yellow? So increasing the concentration of H3O plus ions. So let's see that. So A, if I increase the concentration of the H3O plus, the system will want to decrease the concentration of the H3O plus by favoring the reverse reaction. That means it's going to appear more red. So that's not what we want. We want yellow. If you look at B, if you increase the temperature, so increasing the temperature favors the endothermic. The endothermic is the reverse reaction. So reverse is favored. That means it's going to appear red again. So that's out. If you look at C, if we add a base, so what does adding a base do? So adding a base basically means we are increasing the OH minus, but since there's no OH minus, we can think about what does a base do. A base is a proton acceptor. So in other words, if I'm increasing the OH minus, I am decreasing the H3O plus. So let's look at what happens. If I decrease the H3O plus, the system will want to increase the H3O plus. That's going to favor the forward reaction, and the forward reaction is yellow. So we're going to have a yellow color. That's what we want. The answer is C. Question 1.8. The expression for the equilibrium constant Kc of a hypothetical reaction is given as follows. Which of the following equations for a reaction at equilibrium matches the above expression? Okay, so we'll go one by one here. P2, 3Q2. Okay, we can just write out the expressions. So this one is going to be, remember Kc is product over reactants. So this is going to be, product is PQ3 squared over, and here we're going to have two reactants. This one only has one, so A is out. If I look at B, I have two products, whereas the question only has one product, so B is out. If I look at C has two products. My question only has one product in my numerator, so C is out. That must mean by process of elimination, D is going to be my answer. Now, why is D accepted even though it has two reactants. That's because one of the reactants is a solid and the concentration of a solid remains constant, so it's not going to change. So we exclude it from the Kc expression. So the answer is D. This is question 1.8. Question 1.9. Which statement best describes the difference between endpoint and the equivalence point in a titration? A, the endpoint occurs when the acid or base completely reacted with each other, while the equivalence point is when the indicator changes color. It's actually the opposite, so A is out. The equivalence point occurs when the acid or base has completely reacted with each other. Yes, that is true. While the endpoint is when the indicator changes color. Yes, that is correct. So 1.9, the answer is B. 1.10, a titration experiment was conducted using sodium hydroxide, standard solution of concentration 0.1 moles per dm cubed, and HCl of unknown concentration. In each titration, a volume of 20 cm cubed of NaOH was used. The readings from the burette are given in table below. Okay, what is the concentration in moles per dm cubed of the HCl required to neutralize the NaOH? So what we need to do is we need to first figure out what is the volume of the HCl that we used. So you have 3 different experiments, 3 different titrations, so you take the average. So the average volume, you add up all of them and you divide by 3, you're going to get an average volume of 26.59 cm cubed. Right? Now what you can do is you can use your titration equation. So since this is a reaction, we should know NaOH plus HCl gives us NaCl plus H2O. And everything is in a ratio of 1 to 1 to 1. And so since we know the values, we can calculate the concentration. So we can say that CAVA over CBVB is equal to NA over NB. NA over NB is going to be 1 over 1. The concentration of the acid, so we don't know that, so that's going to be unknown. The volume of the acid that we used was 26.59 divided by the concentration of the base, they tell us is 0.1, and the volume of the base, they tell us to use 20 cm cubed, so 20. Now all we need to do is we need to solve. So 0.1 times 20 divided by 26.59, that's going to give us an answer of Ca is 0.075. So 0.0752 actually, so that means our answer is A. The letters A to H in the table below represent organic compounds. Okay, so we have all of our organic compounds. Let's go one by one. 2.1 says consider compound H. Okay, compound H. All right. Is this a primary, secondary, or tertiary alcohol? And explain our answer. So 2.1, we want to make sure that when we are identifying a primary, secondary, or tertiary alcohol, we are looking for the OH, we are looking for the carbon that it's bonded to, and we are looking at how many carbons that carbon is bonded to. Okay, so in this case, there's my OH. My OH is bonded to a carbon, and that carbon is bonded to 2 other carbons. So since it's bonded to 2 other carbons, it is a secondary alcohol. And why? What is the reason? It's because the OH is bonded to a carbon that is bonded to 2 other carbons. Now 2.2.1, write down the letter that represents each of the following. So a ketone. Okay, so 2.2.1, I'm looking for a ketone. I'm looking at, okay, so I'm looking at this G standing out to me because I see here that there is a double bond O in the middle of the compound, or somewhere in the middle of the compound. So that actually makes it a ketone. So that answer is G. 2.2.2, a molecular formula of a hydrocarbon. So molecular formula meaning I am eliminating H, G, F, E, D, and C because Those are not molecular formula. I'm looking at either A or B. Now, a hydrocarbon is a compound that only has hydrogens and carbons. B has oxygen in it, so that's not a hydrocarbon, so the answer is A. 2.2.3, a reactant in the preparation of compound C. So compound C is ethyl butanoate. So if I consider ethyl butanoate, that is an ester. So ethyl butanoate, that is made up of two compounds. One is an alcohol. The alcohol is ethanol. And the other compound is going to be the carboxylic acid, butanoic acid. So I'm looking for an alcohol. Let's see. So E is an alcohol, but it's not ethanol. So I'm also then just looking for butanoic acid. F is carboxylic acid. However, F has 1, 2, 3, 4, 5, 6 carbons. So that's not going to be the option. However, if I look at option B is C4H8O2. So C4 meaning there's four carbons, and O2 indicating that there's two oxygens. Carboxylic acids have two oxygens, and so the option I'm going to go with here is B. 2.3. So question 2.3, point 1. Write down the structural formula. So structural formula means they want you to actually draw it with all of the bonds and all the atoms and everything. Compound D. So compound D is CH3, CH, CH. Okay, so we can do this. So CH3, we'll just start with that. So I'm going simple, left to right. Then there is a CH. Then there is another CH. Then there is a CH2. And then there is a CH3. Now I just need to go back and make sure that every carbon is making 4 bonds. These two, this one here and this one here, is actually making 3, so I can add a bond here to make it an alkene, and now there's 4 bonds all the way through. Next one, 2.3.2, the functional group of compound F. So if I look at compound F is my carboxylic acid. Well, it is a carboxylic acid. They want the functional group of a carboxylic acid, which is simply the C double bond O and the OH. 2.3.3, the functional isomer of compound G with a prefix of 4-methyl. Okay, so compound G is a ketone. Okay, so the functional isomer of a ketone is an aldehyde. So if I count the number of carbons in G, there's 1, 2, 3, 4, 5, 6, 7. So there are 7 carbons. And so I just need to draw an aldehyde with 7 carbons, and they've given me a restriction. There must be a 4-methyl, meaning on the 4th carbon, there should be a methyl group. So let's draw it in. So carbon 1, carbon 2, carbon 3, carbon 4. On carbon 4, there should be a methyl group. So that's 1, 2, 3, 4, 5 carbons, 6, and then 7. Now, we just need to make sure that it is an aldehyde. So on the first carbon, I need to have my double bond O with my hydrogen, and then just fill in the rest of the hydrogens. There's a hydrogen here, here, just making sure that every carbon is making 4 bonds, and those bonds are to other hydrogens or other carbons. And so that's my answer. Question 2.4 reads, write down the IUPAC name. Okay, so they want the name basically of compound D. So 2.4.1, let's look at compound D. So D, okay, we've drawn it, so it's not a problem. We can name this. So this is an alkene. So the rule when you're naming an alkene is you name closest, or from the carbon closest to the double bond. So we're gonna number it this way. So this is going to be 1, 2, 3, 4, 5. And so this is going to be a pent, because there's 5 in there. the double bond is on the second carbon, so pent 2-ene. Then 2.4.2, write down the IUPAC name of compound G. So compound G is, it is the ketone, so we know it's going to end in -one. Now, when you're naming a ketone, it's important, obviously, to make sure that the ketone gets the smallest possible number. So we have two options, I think, to number it. So let's go with some different colors here. I can go this way. And if I did that, then the double bond O is going to appear on 1, 2, 3. It's going to appear on carbon 3. However, if I went the other way, it's going to appear on carbon 1, 2, 3, 4. So this is the correct order. So going from right to left. So it's going to be a, well, let's count the number of carbons. So there's 1, 2, 3, 4, 5, 6. So it's going to be a hex 3-one. And then also, we can't forget about this. There is a methyl group on carbon number 4, so it will be a 4-methyl hex 3, or hexane 3-one rather. Hex, yeah. I think hex 3-one is okay. Hex 3-one, yeah, that's fine. Let's move on. So hex 3-one or hexane 3-one, I don't think it'll be too much of a problem. Let's move on. Question 2.5.1. Consider compounds E and H. Okay, so let's look at E. E is butane 1-ol. Okay, it's an alcohol. They want to know, identify the type of isomer. So E and H. Okay, so they're both alcohols. Butane 1-ol will have the OH on the first carbon, and this one has it on the second carbon. So this is a positional isomer. It is a positional isomer, and 2.5.2, they want to define this type of isomer. So positional isomer or isomers are basically compounds with the same molecular formula, right? But different positions of the functional groups. So the OH in one of them is on the first carbon, and the other one is on the second carbon. And actually, I think for 2.4.2, let's write it with its traditional name. We'll go hexane 3-one. So not forgetting the hexane, because it's all single bonds. Okay. Yeah, let's move on to question 2.6. Question 2.6.1 says, consider compound C. Okay, where's compound C? Okay, ethyl butanoate, we've spoken about this. To which homologous series does it belong? So it is an ester. 2.6.2, give the name of the catalyst required to prepare an ester. So to prepare an ester, you need concentrated H2, well, they want the name, so concentrated hydrochloric acid. Concentrated sulfuric acid, I think. Wait, just give me a second, let me think. You need concentrated sulfuric acid, not hydrochloric acid. H2SO4, sulfuric acid. Yeah. H2SO4. And 2.6.3, draw the structural formula of compound C. So they want us to draw this. So when you're drawing an ester, just think of cocoa bonds. So CO, CO. So this part is the alcohol, and then this part is the carboxylic acid. So the alcohol, as we mentioned before, is ethanol. So is it ethanol? ethanol. So ethanol has 2 carbons. So we're going to have, that's 1 carbon, then we'll have another carbon, and we will complete this with hydrogens. And then the next part, the carboxylic acid. If you go back here, butanoate, so 4 carbons, this is 1, then the second carbon, the third carbon, and the 4th carbon. Now again, we just complete with our hydrogens. Okay. Let's take a look at question number 3 now. Question number 3 says, the factors that affect the vapor pressure of different organic compounds are investigated. The table below shows the vapor pressure of 5 organic compounds represented by the letters A through to E. We leave out 3.1. 3.2, write down the homologous series to which compounds A and B belong. So A is propane and B is butane. They end in ane, and so they're going to be alkanes. 3.3, explain the decrease in vapor pressure from A to B as indicated in the table. So A and B are alkanes, and alkanes have London forces, right? So A and B. Now with London forces or van der Waals forces, as you increase the molecular mass or you increase the length of the chain, the intermolecular force increases. So B will have a stronger intermolecular force because it is a longer chain. And if the intermolecular force increases, it means that the boiling point is going to increase. So the boiling point of B is going to increase. That means the vapor pressure of B is going to decrease. Because remember, vapor pressure and boiling point are opposite to each other. Question 3.4.1. Compounds C and E are functional isomers. So C and E, ethyl methanoate and propanoic acid. Define molecular formula. Okay, we leave that out. 3.4.2. Which compound will have a higher boiling point? So ethyl methanoate or propanoic acid? It's going to be E, propanoic acid. And 3.4.3 wants us to explain why. Because E, propanoic acid, is a carboxylic acid. Carboxylic acids have hydrogen bonds, which are strong. Right? If you look at C is an ester. Esters have dipole-dipole, which when you compared to hydrogen bonds are weaker. So the one with the hydrogen bond is going to have the higher boiling point. And the ester, since it has dipole-dipole, it's weaker than hydrogen bonds, it's going to have a lower boiling point. Okay, question 3.5. The percentage composition of some of the elements in compound D is given as, okay, so you have 61% carbon, 11.86% hydrogen. Determine with calculations the empirical formula of compound D. So 3.5, for empirical formula, we'll always start by assuming a mass. So assume 100 grams. So that means if you have 61% carbon, it means that you have 61 grams of carbon. From here, you can calculate the number of moles. Number of moles is equal to mass over molar mass. 61 divided by 12, and that's 5.08 moles. Now we can do the same for the other elements as well. So hydrogen is 11.86%, which means it's 11.86 grams. The number of moles is going to equal 11.86 divided by 1, which is 11.86 moles. And they tell us that some of the elements of compound D is an alcohol. Alcohols have oxygen as well. So that means the last element must be oxygen. So the balance of the percentage, so 100 minus 11.86 minus 61 is 27.14% oxygen. That means 27.14 grams of oxygen. Then the number of moles is going to be 27.14 divided by the molar mass of oxygen, which is 16. So 27.14 divided by 16 is 1.696. Now from here, we divide by the smallest number, which is 1.696, divided by 1.696, divided by 1.696. And so we get rounded values of 3, 7, and 1. So that means my formula is going to be C3H7O1, though it's not necessary to put the 1. And so this is my empirical formula. 3.6, write a balanced equation using molecular formula for the complete combustion of compound A. So 3.6, compound A is propane. So propane is C3H, 3 times 2 is 6, plus 2 is 8. And then combustion means you are reacting it with oxygen. And since it's a organic compound with carbons and hydrogens, you're going to get CO2 plus H2O. Now, to balance, we'll balance the carbons first, so I'll put a 3 here. Next, I'll balance the hydrogens, so I'll put a 4 here. And then last, I'll balance the oxygens. There's 2 on this side, there's 6, 10 on that side, so I'll put a 5 here, and so everything then should be balanced. Okay, let's move on now to question number 4. Question number 4 says, the flow diagram below shows how an alkene can be used to prepare other organic compounds. The letters J to N represent various organic reactions. Okay, so question number 4, is an alkene a saturated or unsaturated? So an alkene is going to be unsaturated, so 4.1. And that's because it contains double bonds. 4.2, write down the type of reaction represented by J. So the way I answer this is, if I know that this is an alkene, I call this a 2, and butane is an alkane, so I call that a 1. So a reaction that goes from 2 to 1 is a type of addition reaction. A reaction that goes from a 1 to a 2 is called an elimination reaction, and a reaction that goes from a 1 to a 1 is called a substitution reaction. So if I'm looking at J goes from a 2 to 1, so in that case it's an addition reaction. 4.2.2, K. So K represents you going from a 1, and we don't know what compound Q is, but we can figure it out. So if you look at this reaction here, so let's highlight it, this one here. You take this alkene and you react it with HBr. So you are going from a 2 to a something. From these options, there is no option that goes from a 2 to a 2. So this compound must be a 1. It must be saturated. So reaction K goes from a 1 to a 1, which must make it then a substitution reaction. Then 4.2.3, M. So they want to know what M is. Okay. M is going from a something to a 2. So the only one that goes from a something to a 2 is an elimination reaction. So we don't even have to know that much of detail about the reactions. We just got to know, we just remember the important bits, which are 2 to 1, 1 to 2, and then 1 to 1. And then you can figure out the type of reaction. 4.3, write down the structural formula of compound R. So they want us to draw. So compound R is this compound here. Okay, so what's happening? We have our alkene. Let's draw our alkene. So CH2, the double bond, CH, then we have CH2, then we have CH3. And we are adding HCl. So two things will happen here. The double bond will break. So when this double bond breaks, just let me copy this. Copy and paste. So first thing is that the double bond is going to break. So that's going to break. And now we're going to have two things that are going to be attaching. So you're going to have an attachment here and attachment here. So you're going to have a hydrogen and you're going to have a chlorine. The hydrogen will go to the carbon with more hydrogens. So this hydrogen is going to go here. And the chlorine is going to go here. So that's going to be the structural formula for compound R. Compound R is the major product. 4.4 for reaction N. So reaction N, write down the type of addition reaction. So you are going from an alkene and you are going to an alcohol. So from an alkene to an alcohol, that's called hydration. 4.4.2, two reaction conditions you need for hydration. You need excess water. And the other condition is that you need a little bit of acid, so H2SO4. 4.4.3, for reaction N, write down the IUPAC name of the alcohol that forms. So again, let's just copy this. Well, paste. So this was my alkene. Now we are adding water. So if you're adding water, you are adding two things. You are adding an H and an OH, because water is H2O. So again, just like before, the hydrogen will go to the carbon with the most hydrogens, and then that means the OH is going to fill in the other space, like so. And they want the name of this. So the name of this is going to be butan 2-ol. Now, 4.5, write down the IUPAC name of an isomer of butane. So butane is 1, 2, 3, 4. 4 carbons. Now, I can get an isomer if I take this and I move it here. So, for example, an isomer would be 2-methyl propane. That would be an isomer of butane. Question 4.6. Use structural formulae to write down a balanced equation for reaction L. So reaction L, you are going from an alcohol. We know the alcohol, it's butan 2-ol. And you are going to compound Q, which is going to be something. Okay, so let's first figure out what compound Q is going to be. So you are adding HBr to our original compound. So HBr, we are going to be taking away that double bond. We're going to be putting in a hydrogen here and a bromine that's going to go there. So this is my compound Q. This is going to be my product. Right, so there. Now it's a bit tight for space, but we'll make do. So let's just draw it this way. Now the alcohol was butan 2-ol, so 1, 2, 3, 4. Hydrogen, the OH was here. So now what would we need to ensure that we take out the OH and we replace it with a Br? So if we reacted this with HBr, then the bromine would then attack or be substituted with this OH, and so we'll get a Br here, and the byproduct of this would be, since the OH is coming out, you're going to have the hydrogen forming with the OH, you're going to get H2O. So that's our structural formula. Question 5 says 3 different experiments are performed using the reaction between magnesium carbonate and hydrochloric acid. Experiment 1. In this experiment, magnesium carbonate reacts with excess hydrochloric acid in a closed container at 23 degrees Celsius. The reaction is monitored by measuring the volume of carbon dioxide gas produced over time. The molar gas volume at 23 degrees Celsius is 24 dm cubed. The data collected is shown in the table below. we'll leave out 5.1. 5.2, use collision theory to explain the effect on the reaction rate as time progresses. So basically what's happening when you do rates of reactions, you'll learn that at the beginning of any reaction, the reaction rate is quite high. And that's because at the beginning, you have a lot of reactant, right? And you have these reactants that are in this vessel or in this container. And so there's going to be frequent collisions, and you're going to have, so frequent collisions, and you're going to have a high rate. And this is at the start. However, as time progresses, the number of reactants decreases. So the reactants will decrease because they're being used up. You're going to have fewer collisions per unit time. And that will mean that you're going to have a lower rate. And so as the reaction progresses, the rate of the reaction will decrease. Question 5.3, calculate the rate or the reaction rate for the production of CO2 during the first 20 seconds. So rate in this case is going to be the change in the volume divided by the change in the time. So they want the question is saying in dm cubed per mole, they've given us here cm cubed. So we need to remember the conversion cm cubed to dm cubed. We need to divide by 1,000. So we'll say the time at the volume at 20 seconds is 300. So that's 0.3 minus 0 divided by 20 minus 0. It's just like coordinates calculating the gradient. It's basically the same thing. And then that's going to give you 0,015 dm cubed per second. Question 5.4, calculate the mass of magnesium carbonate required for this experiment. So 5.4, what we can do is we can say that there was 500 cm cubed of CO2 produced. So the volume of CO2 is 0.5 dm cubed. Now we know the molar volume is 24, so we can get the number of moles. So number of moles is equal to V divided by Vm, 0.5 divided by 24, which is 0,02. Now we can do the mole ratio, and the mole ratio of CO2 to magnesium carbonate is 1:1. So therefore, the number of moles of magnesium carbonate is also going to be 0.02. Now that we know the number of moles, we can calculate the mass. So mass is equal to number of moles times molar mass. Number of moles is 0.02 times the molar mass of magnesium carbonate is 84. And that gives you 1.75 grams. Now experiment 2. Experiment 1 is repeated, but this time at 30 degrees Celsius. So at a higher temperature. The following Maxwell Boltzmann distribution curve was produced. Which graph A or B represents experiment 2? So experiment 2 is going to be B. And why is it B? That's because two reasons. The peak shifted to the right. Right, so if you look at it, this was the first one. That's the second peak. It shifted to the right and it shifted down. So that's something you need to look for. At higher temperatures, when you're studying the Maxwell Boltzmann curve, at higher temperature, the peak will shift to the right and it will shift down. And the other thing to look out for is that you have a greater area. And remember that area is going to be the number of particles. So basically you have more particles now that have kinetic energy that's greater than activation energy. So if you study this graph, this curve, you can see that there's a much greater area here for B. So the greater area means that it's going to be at a higher temperature. And then 5.5.3, if a catalyst is added, would the line move to the left or right? So it's going to move to the left. And why? Because a catalyst reduces the activation energy. reduces the activation energy. Though they didn't ask us to explain it. We just did. Now experiment 3 says, experiment 1 is repeated, but a catalyst is added, and the following graph is obtained. Is the graph, or is the reaction exothermic or endothermic? Here it's just easier if you just know the shapes. An exothermic graph looks like this, an endothermic graph looks like that. So endo, this graph is exothermic, just from the shape, right? 5.6.2, which letter represents the activated complex? Here you could go B or D, since the question wasn't specific. The activated complex is this region here. Then 5.6.3, give the value of the activation energy for the forward catalyzed reaction. So the catalyzed reaction is this dotted line, and activation energy is equal to the energy of the activated complex minus the energy of the reactants. So that's going to be 75 minus 65, which is 10 kilojoules. So question 6 reads, the reaction between carbon disulfide and chlorine gas reaches chemical equilibrium in a closed container at constant temperature. The products that form are carbon tetrachloride and sulfur dioxide, or dichloride rather. The balanced equation for this reaction is given below. Initially, an unknown quantity of CS2 and 5 moles of Cl2 are placed in a 2 dm cube container and allowed to reach equilibrium. The equilibrium mixture contains 0.8 moles of CCl4. The equilibrium constant, Kc, for this reaction is 0.36. We leave out 6.1. 6.2 says calculate the initial number of moles of CS2 required. I'm looking at the mark scheme, 8 marks, and that's telling me one thing. It's telling me that I need to use a Rice table. So let's construct our Rice table. So RICE, and we will write out the different quantities that we have. So first thing is the CS2. Then we have Cl2. Then double line because I want to separate the reactants and products. Then I have CCl4. And then I have S2Cl2. Now R is ratio. So what is the ratio of these elements? This you get from the coefficients. So in front of CS2, there's an imaginary 1. In front of Cl2, there is a clear 3. In front of CCl4 and S2Cl2, they are invisible 1s. Now, initially, we don't know how much of CS2 is required. So let's make that X. Cl2, they tell me in the question that we have 5 moles of Cl2. And since it's at the beginning of the reaction, we don't have any products. So that's going to be 0 and 0. Then they tell us it's in a 2 dm cube container. Okay, so this is going to be important. And they tell us the equilibrium mixture contains 0.8 moles of CCl4. So 0.8 will go here. E is equilibrium. That's how much we have at equilibrium. Now, the row that has C in it, this one, is I think the most important row. It's the row that represents the change. So how much did this change by? So it increased by 0.8. And now this row, the C row and the ratio row, they go together. So in other words, since the ratio here is 1 to 1, if this increased by 0.8, this is also going to increase by 0.8. So that means 0 plus 0.8 is 0.8. Now, since the ratio here is 1 to 1 as well, this is also going to be 0.8. But since this is a reactant, it's going to decrease by 0.8. And so I'm going to have X minus 0.8 here. Now the ratio again, since the ratio is 1 to 3, this is going to be 2.4. So 0.8, 0.8, 0.8 is 2.4. Since it is a reactant, it's a minus. So 5 minus 2.4 is 2.6. That's why I use this double line, just to separate the pluses and the minuses. So we've got the equilibrium values. Now we just need concentration. We can use Kc and then solve for x. So now we know the volume is 2. So to get the concentration, all we need to do is divide the number of moles by 2. So now this is like an extension of the Rice table. So the concentration here is going to be x minus 0.8 over 2. This is going to be 2.6 divided by 2 is 1.3. That's going to be 0.4. That's going to be 0.4. Now, next thing to do is to construct my Kc. So Kc is equal to concentration of products divided by concentration of reactants. Now my products are going to be S2Cl2. The ratio is 1, so the number in front of it is 1, so the exponent is 1. Then CCl4 divided by the concentration of CS2, and then the concentration of Cl2, and then since there's a 3 in front here, there's going to be a power 3. Now we just substitute. We know the Kc. The Kc is 0.36. That's equal to, so we have 0.4 here, then 0.4, then we have x minus 0.8 over 2, and then we have 1.3 to the power of 3. And now we can solve for x. X is the only unknown. So we solve for x, and we get x is 1.205 moles. And that is the number of moles that we needed at the beginning. Now, question 6.3, how will each of the following changes affect the yield of S2Cl2 at equilibrium? So they want to know how is it going to affect the product. Right, increase or decrease, and give a reason in terms of which reaction is favored. 6.3.1, if carbon tetrachloride is removed. Okay, so if we decrease the carbon tetrachloride, the system will want to increase the carbon tetrachloride. Since the carbon tetrachloride is on the right hand side, the forward reaction is favored. If the forward reaction is favored, it means that the S2Cl2 will increase. Now 6.3.2, the volume of the container is increased. If I increase the volume, I am decreasing the pressure. Now if I decrease the pressure, the system will want to increase the pressure. And how does the system increase the pressure? It favors the side with more molecules, more gas molecules. So if I look at the left hand side, I have 3 here and 1. I have 4 total. If I look at my right hand side, I have 1 and 1. I have 2. So the side that has more is going to be the high pressure side. The side that has less is going to be the low pressure side. So it's going to favor the side with more molecules. It's going to favor the left hand side. So the reverse reaction is favored. And so the S2Cl2 will decrease. All right, let's move on. Question 6.4. The graph below shows the changes in the rate of the reaction after further changes were made to the equilibrium mixture above. 6.4.1, the equilibrium was disturbed at 5 minutes due to a change in the concentration of CS2. Was this concentration increased or decreased? Now, I'm answering this based on what I'm seeing in the graph. I'm seeing that the rate decreased. And I know from rates, one of the factors that affects the rate is the number of molecules or the number of particles. If we decrease the number of particles, or decrease the concentration, then the rate is going to decrease, because collision theory says that fewer particles, fewer collisions, lower rate. So I'm going to go here and I'm going to say that it was decreased. And that's because if I'm looking at the graph, I'm seeing that the rate decreased. 6.4.2, at 15 minutes, the temperature was changed. Use Le Chatelier's principle to determine whether the temperature was increased or decreased. So we don't need to use Le Chatelier's principle here. All we need to do is look at the rate. what happened to the rate. So the rate increased. It went from here, it went there. And again, according to collision theory, if the temperature increases, the rate will increase. So the temperature increased. But now they do want us to explain, so we can use the Chatelier's principle to kind of explain what we are observing. So if you increase the temperature, the endothermic reaction is favored, right? And both rates will increase, right? But the endo reaction is favored. Now, if I look at the reaction, the forward is exo, that means the reverse is endo. So that means my reverse reaction is favored. That means the reverse reaction will increase more than the forward. And that's what if you look at the dotted line, the reverse reaction is the dotted line. The reverse reaction is increasing much more than the forward. Okay, let's round up now and go into question number 7. Question 7 says oxalic acid is an organic diprotic acid commonly found in plants such as spinach. It's used in various industrial and lab applications, including cleaning, bleaching, and as a standard solution in acid-base titrations. When oxalic acid ionizes in water, it follows the steps given below. Okay, we'll leave out 7.1. We'll go straight to 7.2. Identify the acid-base conjugate pair in step 1. Now here you have a choice. You could go the easy one, which is going to be H2O and H3O plus. It could be H2C2O4 and then HC2O4 minus. You could choose that as well. It's also an acid-base pair. 7.3, give a reason why oxalic acid is referred to as a diprotic acid. It's because it can donate 2 protons. So if you look at the steps here, there's 2 steps, and in each step is donating a proton. So it can donate 2 protons, hence the term diprotic. Question 7.4. The oxalate ion can act as an ampholyte. Give a reason for the statement. So this HC2O4, this oxalate ion, it can, an ampholyte is something that can act as an acid and a base, or a base. An acid is a proton donor, so it can act as an acid. And it can donate the proton. It can form C2O4 2 minus, like it's showing in step 2. Or it can act as a base, and it can accept a proton. If it accepts a proton, it's going to form H2C2O4, like what we are seeing in basically the reverse of step 1. Question 7.5.1. In a volumetric flask, 2.25 grams of oxalic acid is added to water to make up a standard solution to 250 cm cubed. Calculate the concentration of the oxalic acid. So here we can use the formula C is equal to M over capital M times V. The mass is 2.25. The molar mass of oxalic acid is 90. And the volume that they're making this in is 0.25 dm cubed. That gives us a concentration of 0.1 moles per dm cubed. Moving on, 7.5.2, 25 cm cubed of the oxalic acid solution is titrated against sodium hydroxide. The average volume of NaOH required for neutralization is 28.6 cm cubed. Calculate the concentration of the sodium hydroxide. So here what we can do is we can use a formula for titrations. So CAVA over CBVB is equal to NA over NB. Now, we worked out the concentration of the oxalic acid. It's 0.1. The volume, they tell us here, is 25. And we don't need to convert it if we're using this formula. Divided by CB, which is the concentration of the base, that's what we want. And they tell us the volume is 28.6. and that's equal to Na over Nb. We get that simply from the coefficients here. So the acid has an invisible 1, so 1 over, and the base has a 2. Now we just solve for Cb. So Cb is going to be 0.175 moles per dm cubed. 7.5.3, explain why phenolphthalein would be a suitable indicator. So phenolphthalein is sensitive to pH ranges that are greater than 7. If you look at the reaction that we have, NaOH is a strong base. Oxalic acid is a weak acid. And so the salt is going to be a basic salt, meaning the pH of the salt is going to be greater than 7. Hence, using phenolphthalein would make sense. 7.6, question 7.6 reads, the reaction between excess magnesium hydroxide, a slightly soluble base, and nitric acid occurs in aqueous solution, where it produces magnesium nitrate, a soluble salt, and water, according to the following balanced equation. 0.05 dm cubed of magnesium hydroxide solution has a concentration of 0.115 moles per dm cubed and is added to 0.025 dm cubed of a 0.095 moles per dm cubed HNO3 solution. Okay, calculate the pH of the final solution. Okay, 10 marks, a lot of things that we have to do here, but first let's start off by figuring out what our answer should look like. So one of the key things is that they're telling me that there's an excess amount of magnesium hydroxide. Magnesium hydroxide is a base, and so since there's an excess amount, it means that there's going to be some left over. If there's some left over, it's going to affect the pH, meaning that the pH at the end should be greater than 7. Now what we need to do is we need to figure out how much of MgOH2 is left. So that is the key question here. So we'll start off, first thing, by saying how much did we start with. So we started with, we can do number of moles is equal to Cv. They've given us the concentration. The concentration is 0.115. The volume is 0.05. That gives me a number of moles of 0.00575. Next we'll do, how much did we need? How much did we need? So to do this, we'll calculate the number of moles of the acid and then do a mole ratio. Now if you look at the mole ratio of the acid to the base is 2 to 1. In other words, I need half the amount of acid to neutralize the base. So I will say the number of moles that I need is going to be half of the number of moles here. So to calculate number of moles of the acid, I'm going to do Cv again. So 0.095 times 0.025, and that's going to be 0.001185. That's how much I need. So how much is left? That's going to be 0.00575 minus 0.001185. That means I have 0.004625 moles left. Now this, must understand, is in a container, right? And now the total volume of the container is going to be how much we had of the base and how much we had of the acid. So we had 0.025 and then we added in 0.05, and so now the total amount of liquid that's in there is going to be 0.075 dm cubed. Now we can calculate the concentration of this. So step number 4 now would be the concentration of the magnesium hydroxide. That's going to equal 0.0045625 divided by the volume, 0.075, and that is equal to 0.06 moles per dm cubed. And this is of magnesium hydroxide. Now remember, magnesium hydroxide, when it's in the solution, is going to dissociate. So magnesium hydroxide, when it breaks up, you're going to get Mg2 plus and you're going to get 2 OH minus. If the concentration of this is 0.06, then the ratio here is 1 to 2. That means the concentration of this, which is what we're interested in, that's going to be 0.12. Now that we know the concentration of this, we can calculate the concentration of H3O plus. Remember the equation? Kw, now this I think is step 6 now. Kw is equal to the concentration of H3O plus times the concentration of OH minus. This is 1 times 10 to the minus 14. This H3O plus is what we want. And then OH minus is 0.12. And the reason why we need this is because remember, to calculate pH, that's minus log of the concentration of H3O plus. So we can calculate the concentration of H3O plus here, and it's going to be 8.2 times 10 to the minus 14. And now the last step, of course, calculate the pH. It's going to be minus log of 8.2 times 10 to the minus 14, and that gives me an answer of 13.09, which is what we expected from the beginning. We expected a pH greater than 7.